Solve the system x plus 2y plus z equals 3, 3x minus y minus 3z equals minus 1, and 2x plus 3y plus z equals 3 using the method of elimination. Let's begin by writing this system of equations as an augmented matrix. The first row would read 1, 2, 1, 3. The second row would read 3, minus 1, minus 3, minus 1. And the third row would read 2, 3, 1, 3. Now the basic idea of elimination is to try to reduce this matrix by putting in lots of zeros in strategic places. Specifically, we want zeros here, here, and here. Now I'm actually going to go and work this thing out into what's called its reduced row echelon form, which is to put as many zeros in it as possible, and it's good practice with our row operations. But let's start by getting this thing in row echelon form first. Notice that we have a number here, so to get zeros in the two entries below, we can scale the first row and add it to the other rows. For example, if we were to scale the first row through by minus 3 and add it to the second row, we'd get a 0 here. The first row scaled through by negative 3 would be minus 3, minus 6, minus 3, and minus 9. And if I were to add these two values together, term by term, we would obtain the row 0, minus 7, minus 6, minus 10. Similarly, if we scaled the top row through by negative 2 and added it to row 3, we would get a 0 in the leading term. The top row scaled by negative 2 is minus 2, minus 4, minus 2, minus 6. And so adding these together, we have 2 minus 2, 3 minus 4, 1 minus 2, and 3 minus 6. And of course, the top row we're leaving unchanged, so we have that leading value. It's worth noting that each of these two rows have a factor of minus 1, so I can scale both rows by a negative 1 to obtain the matrix 1, 2, 1, 3, 0, 7, 6, 10, and 0, 1, 1, 3. I'll also point out that it's been my experience that having a 1 as a pivot is a lot easier than having other numbers. So let me swap these two rows around, like that. Next, we need to get a 0 down here. We could do that by scaling the second row by a negative 7 and adding it to the third row. If we scale the second row through by negative 7, we would have 0, negative 7, negative 7, and negative 21. And then adding those two values together, we would have 0 plus 0, 7 minus 7, 6 minus 7, and 10 minus 21. The other rows remaining unchanged. Note that we can also scale the bottom row through by a minus 1 to obtain this. And this puts the matrix in row echelon form, since the pivots now live along the main diagonal. However, let's practice reducing this further. Let's see if we can get zeros above our pivots as well as below. Now, if I take the bottom row and scale it by a minus 1, I could add it to the two rows above it to get zeros in that third column. Specifically, the bottom row multiplied by negative 1 gets me 0, 0, minus 1, minus 11. And I could add this to both of the rows above it to obtain the matrix 1, 2, 0, minus 8, 0, 1, 0, minus 8, and 0, 0, 1, 11. I can also get a 0 above this pivot by multiplying the second equation through by 2 and adding it to the first equation. Scaling the second row through by negative 2 gets me 0, minus 2, 0, 16. And adding that to the top row yields 1, 0, 0, 8, 0, 1, 0, minus 8, and 0, 0, 1, 11. Note that each one of these equations is now simple to translate. The top equation says that x is equal to 8. The second line says that y is equal to minus 8. And the third line reads z equals 11. And so we've been able to decode the solution directly from the row-reduced matrix. It's worth checking these values by substituting them back into the original three equations. And I leave that as an exercise to you.